Now finite volume. So the first thing about finite volume is conservation law PDEs. That's because finite volume, unlike finite difference, is not suitable for solving any PDEs. Finite volume is a specialized scheme. It specializes in solving conservation law PDEs. So first of all, you have to know what conservation law PDEs are. So it is du dt, and u represents the density of a certain conserved quantity. Okay, it is plus df of u dx equal to a source term, okay, or equal to 0 if there is no source term. That's in 1D, and in 2D and 3D, instead of just the spatial derivative, you have the divergence of a flux vector equal to s. So these are the kind of conservation law PDEs. And the conservation law PDE has a primitive form and a conservative. So what we have written down is the conservative form, and the primitive form is just taking use the chain rule to say, okay, df dx is actually df du times partial u partial x, right? So that's basically taking chain rule. And in this case, in the two-dimensional case, we have this times df, which is a vector, du dot with the gradient of u equal to s. So this is the primitive form. This is the conservative form. And the primitive form is useful. For example, we did a bunch of characteristic line analysis, right? And these are used in the primitive form. And you're going to see that this dfdu is going to be the slope of the characteristic lines on which, along which the solution is constant if s is equal to 0. Right? These are the usefulness of the primitive form. But the primitive form only makes sense in part of the domain. Which part of the domain is it useful? Which part of the domain is the primitive form not useful? So in what cases you cannot apply the chain rule to f? Or the chain rule doesn't make sense? Yes, at discontinuities in the solution. So the primitive form is useful in smooth region of the solution and is useless in discontinuities. And it's not that the conservative form is actually useful in discontinuities. It's actually not, because it also involves derivatives. So in near discontinuous regions, we need a third form, the integral form. The integral form is basically integrating not the primitive form, but integrating the conservative form. It says d dt of an integral over a and b of u dx plus f of u. I mean, the df dx, when you integrate, becomes just the boundary is equal to abs dx. So that's in 1D, and in 2D and 3D, you're integrating over any finite domain. And you have to use the divergence theorem, right? Onto the divergence of the flux, you have the normal, outside normal, dot with the flux. So that's the integral form. Okay, the integral form is the form that leads to the finite volume method. The finite volume method forgets about the conservative form, it forgets about the primitive form, it only uses the integral form. Right, so basically you need to understand how finite volume schemes work. It's basically you split the entire domain. In 1D, you split the entire domain into small intervals you call volumes. And in 2D or 3D, you split the domain into small triangles or quadrangles or whatever shape you want and call them volumes. And you apply this or this onto these finitely many volumes. The application of this is going to be basically exact, and except for that infinite volume, you store not the value of the solution at any particular location, but the integral of the solution or average of the solution over these volumes. By infinite difference, you store the solution at the grid points. Infinite volume, you forget about the grid points. You store these volume averages or volume integrals. And the consequence is that you actually have to approximate this. You have to approximate the value of u, and as a result, the value of f of u at the interfaces. Right, so infinite difference, we store the grid point values and we approximate the derivatives. Infinite volume, we don't have the derivatives because we are starting from the integral form. And we store the averages and we approximate the point values. All right. So this is basically how finite volume works in 1D and 2D. Right. This is basically what you need to know about finite volume. All right. Any questions? No? Okay.